Sherry, did you want to make the announcement now? And just get close to this so the people that are watching the video can hear it.
Okay.
Guys, quiet down for a second.
Hi guys. Today from 3 to 5 and tomorrow, Thursday, from 11 to 1, I'm doing a midterm review in the Learning Center, which is 1300 Boylan. When you walk into Boylan, straight, directly, you just keep walking straight through the building. So I have the midterm review for your test on Monday.
Yeah, that's fine. I mean, they'll have a video too. So again, midterm review, 3 to 5 on Wednesday, and 11 to 1 on Thursday in the Learning Center. So today,
Yeah.
3 to 5.
Yes.
Okay, so the video won't get that. And maybe not tomorrow either. So, all right. So I'm going to go ahead and get started. So, again, what I had sort of said yesterday is, what I'm going to do today is we're going to finish up talking about the last organometallic reaction. This is actually a reaction that I'm fairly familiar with because I did a lot of work on it during my graduate career. But also then afterwards we'll do a sort of a mini review. So if you guys have specific questions of things that you would like me to come up with problems for that we can go over, things that you might be struggling with understanding and so forth, we can do that. So I'll try to cut off metathesis in say 20 minutes or so to give us close to an hour or so to do other things. And so as we learned from, this is going to be olefin metathesis, okay, and olefin is just another way that people say alkene, so it's kind of alkene, maybe we'll just say alkene metathesis, just to keep it confusing. I didn't know what an olefin was until I was in graduate school, so olefin is like an old term, it's just alkene metathesis. And what alkene metathesis is it allows the rearrangement of alkene bonds to form new alkene bonds. And so when we think about a standard process, really what an olefin metathesis is, sometimes it's best to color coordinate this. Is if you can take two alkenes and formally what the process is 2 plus 2 okay, followed by sort of a retro 2 plus 2. So okay, followed by effectively a retro 2 plus 2. And it's reversible. This would be reversible. The net result is that what you have is right, where in this case what we have is a carbon here. Right, and then up here we have our sort of our green or blue. So formally what the process involves is a sort of, so formally what it involves is taking an alkene and effectively rearranging the bonds in order to take two of the carbons in that alkene and make a new alkene bond, and take the other two carbons and make an alkene bond. And so again, the process, at least formally, that you would imagine is taking place through, excuse me, thank you, is a 2 plus 2 followed by retro 2 plus 2. And so it turns out that this, I actually seen a good friend of mine when he was doing a synthesis problem of his, or synthesis, one of his steps, he actually, I think formally did this without metathesis catalyst. In order to do that, what you would need to do, right, is what? Would this 2 plus 2 take place thermally? Right, it's one of the things about Diels-Alder chemistry, right? You need that 4 plus 2. A 2 plus 2, as we discussed, is not allowed, so generally what you need to do, and those 2 plus 2s are light. And so this process, at least thermally, you're not going to be able to do. So you can't really do the sort of overall process of metathesis without what we're going to discuss, which is the metal. Right. What's that? Yeah, so we'll discuss this a little bit. So as drawn, again, it would depend upon the stereochemistry here, but that's a good question. So what you would need, right, is you'd need, I didn't really show the stereochemistry there, but yeah, in that process. But this was just a hypothetical anyway. And what we'll see is in metathesis chemistry, it often leads to the most stable alkene because the overall process is reversible. So it's a sort of thermodynamically driven process. Now, if you can imagine, you can do this, you do have a certain advantage, right? And that's that there's an advantage to this, and that's that what you're generating is ethylene gas, right? And so any reaction that you see where you generate a gas that has certain advantages in terms of driving the process, right? Because the process can be rendered effectively irreversible. Okay, but again, the first problem in this is that this doesn't work. Well, it turns out that probably about 20 to 30 years ago, it really started in the 70s, this sort of discovery was made, and then probably in the 90s, where chemistry was developed further. But it turns out that if you take certain, while sort of carbon-carbon bonds can't formally do 2+2s followed by retro 2+2s, metal carbines are capable of doing this. And again, this has to do with, we're not going to get into the molecular orbital explanation behind it, but if you think about it, metal carbines are able to draw within them, d orbitals and so forth, and so they have the ability, it doesn't necessarily follow the same trends that we often assume other compounds would be. So if you took a molecule like this, and you treated it to a metal carbene, what happens is the metal carbene can actually facilitate this process, because the metal carbene can do the 2+2, retro 2+2 process, so it can do the exact same thing there. Generating a metallocyclobutane. Okay, so this metal can do this. And everything's going to be reversible here. Right? And then what you end up getting is now a new metal carbene when you go through this process. And this new metal carbene now has within it a component of this sort of R1. Right? And the byproduct in this reaction is, again, going to be ethylene gas, so that might, in fact, make this process irreversible, right? So if you generate that ethylene gas, the gas is going to go away. And then what's going to happen is now it can react with your second equivalent of alkene. Right, now we can do that same process again, 2+2 retro 2+2. And the retro 2+2. And that's going to lead to is your metal carbene, you're going to regenerate that. And I'll put a squiggly line there. Because, again, as sort of Ray brought up, this process overall isn't generally going to be a stereoselective process. Okay, so this would be a reaction called a cross metathesis. Because what we have here is two separate alkenes that are going to react together. So, in general, when we talk about the metathesis reaction, when we're talking about an intermolecular, right? We're talking about two separate alkenes. Okay. Now, there's a couple things sort of that are worth noting about this reaction. One of the things that sort of Ray brought up is the stereochemistry here, And in order to get the trans product, generally what needs to happen is you need to have a reversible metathesis process. So, and I'm not going to get into specific details about this, but you know, one of the challenges with cross-metathesis historically is that you'll often get mixtures of E and Z depending upon what the metathesis reaction is that you're running. But formally, the overall process can in fact be reversible, so it's very common that you do get Z-selective processes. So for the purposes of this course, I would just assume that these processes are reversible, and that we will get, sorry, did I say Z-selective? I mean E-selective. So for the purposes of this course, we can imagine that you can get E-selectivity. Again, this is a very new reaction. New catalysts are being developed. Pretty much you'll see them being developed even now on a monthly basis. One of my mentors when I was in graduate school has made really significant contributions to this, and a friend of mine actually developed, along with Nobel laureate Dick Schrock, a way to actually have a catalyst that does Z-selectivity. So this is really a development that's taking place as we speak in terms of making this process more and more efficient. But again, you know, I would just, for the sake of this course, you can just imagine the process being E-selective if, say, for example, you want to use this in a synthesis. Okay. Now, I just sort of shown this as being a metal carbene. There are certain metals that can do metathesis that have been optimized for. And there's really two different classes of these. One of them are molybdenum-based catalysts that were developed by Dick Schrock at MIT. And then there's another class of metathesis catalysts. And I won't talk about the molybdenum-based ones. They're generally not used quite as, they're not generally used as much as the ruthenium-based ones, in part because the molybdenum-based catalysts are a little bit less stable to air and stuff, so you have to like use a glove box to use them. And so in general, I'll just show you some examples of the ruthenium-based ones. So these are catalysts that have been developed that are stable. You can weigh them out in the benchtop. They're stable for years at a time. Well, I don't know about years, but they're stable for a very long time. And again, they've been widely used, and a Nobel Prizes have been given for this. So the catalysts that are largely used are known as Grubbs catalysts, and they're named after a chemist named Bob Grubbs, who's at Caltech currently, and they're all ruthenium-based. And there's really two classes of these that you'll see, and one of them is primarily used for cross-metathesis reactions, and the other one's primarily used for what we would call ring-closing metathesis. And they're very similar in a way. So the catalyst is formally, and there's been different versions of these. These are the sort of classical ones that people consider. And so the sort of first generation catalyst for Grubbs, the one that you'll often see, it looks like this. So it's styrene based. So what you start is with the styrene based on that, but after you go through, and we'll sort of discuss this, after you go through one catalytic cycle, what you have is something that looks more like the free metal. And so this is what's called first generation. And there's also a sort of a second generation metathesis. So this is primarily used for ring closing. This is the sort of go-to for ring closing. It's a little bit less active. Then there's, and a little less stable. And then there is, it's referred to as the second generation Grubbs catalyst. Certainly more complicated. It has this ligand up here. This is a carbene, so we'll often draw it. You could sort of think about it as a carbene at this center, and so the lone pairs and the nitrogens actually donate into there. I'm not going to expect you to draw this, but just I'm making the point that it's it has just a different ligand up here. So it's the same in everything except that it's got this, what's known as an arguing to carbene up here. And this makes it more active. So this is the second generation. Now, one of the things about metathesis catalysts are that the phosphines in the first step in the mechanism actually dissociate, and that allows for an open coordination site where the subsequent alkene will come in to react. So the first step in any metathesis reaction is going to be the generation of phosphine based upon just sort of the phosphine leaving. And the thing that's important about that is that the phosphines are also nucleophilic. And what can happen is the phosphines can actually start to decompose the catalysts. And so one of the things that was actually developed at Boston College, where I did my PhD work, by a guy named Amir Haveda, was he started to develop catalysts, and it actually took place serendipitously. They sort of made this discovery, and it was also based upon some contributions made in the lab that I was in, which was Mark Snapper's lab. And what this new catalyst basically found was that instead of having the phosphine there, it turns out that you can get chelation from the sort of oxygen. So instead of the phosphine making a data bond there, now it's sort of oxygen making a data bond there. And everything else is pretty much the same. But what's important about these types of catalysts, and it's worth mentioning, and then this will be it for catalysts. So this is like probably one of the most currently, like, it's not any more expensive than some of these other ones. It's pretty much the same price, but it's got a lot of advantages. This one's called Haveda drugs. And it's also very, very popular. So this would be Haveda drugs too. And the advantage to Haveda drugs too is that it doesn't have this phosphine in it. And so what can happen is you can begin to use this catalyst, for example, at higher temperatures. Let's say you're trying to get a reaction, you're trying to push it harder. If you might be using this sort of second generation catalyst, that might allow for time for the phosphine to decompose the catalyst. In this case, you don't have the phosphine, and so you can actually go to much higher temperatures with this one, for example. And I think when they were selling it, they were also trying to sell it as the fact that it was more stable so they could actually re-isolate it. So anyway, so those are just some of the catalysts that you'll commonly see. And again, I'm not expecting you guys to draw them. For your guys' sake, you could just draw ruthenium. You know, for the extent that you guys need to know what the catalyst is, you could sort of, at least for now, just abbreviate them all as a ruthenium carbene. And again, that ruthenium carbene is the part where the mechanisms will take place. And so as long as you don't need to memorize these whole structures, I think it's worth mentioning the sort of developments that have been made. These are fairly recent developments. But if you just sort of classify them all as ruthenium carbene, that will at least allow you to get into thinking about the mechanisms and how this process takes place. Okay? All right, so in the final 10 minutes or so, told you guys I was only going to spend 20 minutes. So there's a few different types of metathesis. And again, as we sort of spoke earlier, the mechanism generally involves this is the common mechanism through all of these. Formation of metallics like with butane, and then sort of subsequent rearrangement, right, where you effectively get a rearrangement. And so again, for the final exam, you're going to want to be able to know this, and there's some problems on worksheets that ask the mechanisms of these. And it's a fairly straightforward mechanism. So it's a little bit different than what you've seen, but it's pretty easy to remember, just the 2 + 2 followed by the retro 2 + 2. But what's neat about the metathesis reaction is, despite this simplicity, a lot of complexity can be generated, sort of cascade processes are sent off that make for fantastic mechanism questions. So you can probably expect a really nice metathesis mechanism question on the final exam. So it won't be on this next one, but you can certainly expect one. And given the time, I'll just sort of show some of the ones that I'd like you guys to try to think about on your own. One of them, because they all just involve this overall process. And so, say for example, if you do a ring closing metathesis, right? You should be able to draw a mechanism where if you take a molecule like this, go through this 2 plus 2 retro 2 plus 2, and then what you're going to see is that then there's going to be another 2 plus 2 retro 2 plus 2. What you should be able to get to is cyclic systems that look like this. And so what I would sort of urge you guys to do is when you have some time, maybe after the exam's over, or maybe if you're already ahead and you don't need to study anymore for the exam, you can sort of go through this process and try to convince yourself how this might go to the ring-closed metathesis form. And the other point that I'll make is that this sort of 2 plus 2 retro 2 plus 2 on for alkenes is one thing. There's another class of reactions called ene metathesis. And it's going to be very similar. You're not really going to change anything. The only thing that will change, the only thing that's different between olefin metathesis and ene metathesis is that you're going to have an alkene and an alkyne. Okay? And so in those cases, you'll get a slightly different structure, but you're going to go through that same process, right? You're going to do the 2 plus 2 retro 2 plus 2. But now, instead of generating the metallocyclic butane, you're going to generate metallocyclic butene. Okay? And what you'll notice is that if you continue this process, you now are able to generate, if you just do the analogous thing to what's up there, you're going to generate the same compound, but instead you're going to have, because you have an extra bond here in terms of double bond, you're going to maintain that double bond here. And then this can begin to go into cross metatheses and so forth. And so what you should sort of do, and I'll give you guys as a sort of a problem to try, is simply to convince yourself, if you take a molecule like this, so again, an E9 ring-closing metathesis, and go through this mechanism to try and figure it out, and then on my worksheet I have some even more complex mechanisms, which simply, again, just break it down one step at a time, follow your carbons. It's the same thing, it's just sometimes difficult, I think, for you guys to keep track of all your atoms. But if you go through this process, formally what you'll end up getting is that diene, okay? So with that, well, I guess in this case you would end up with ruthenium out there. But what you'll find is if there's another, say for example, equivalent of an alkene, that will then undergo the cross metathesis. So again, convince yourself of this as well. 1, 2, 3, 4, 5, 6. Yeah, so it'd be that. Okay? So this is what we're going to talk about for metathesis. Again, it's a fairly simple and straightforward, I think, mechanism. Get comfortable with it. Makes for very nice mechanism problems. So be prepared. There will be a mechanism question on metathesis on the final exam. Okay? All right. So with that, that's all that I really wanted to talk about with the metathesis reaction. What? Oh, I know. No, but I told them I would give them more time for the... Mike's looking out for you guys. All right, so, yeah, we're going to do a review. All right, so, as I erase this, you guys can think of questions. All right, so so the question is Orgo 1 material going to be on this exam? Yes. Yeah, I would say synthesis, I'm not going to say it's not. So organic chemistry is additive. There is a lot of material, so I will just say this. There is a lot of material that we covered, and I think a lot of important material that was covered since the first exam. So I have lots of material within there to give you guys on the exam. And so it will be heavily involved in that type of aspect. But specifically, say, for example, a synthesis problem, you may need to pull back on some of those older reactions. So while the emphasis will be on amines and organometallic cross-couplings and metathesis and Diels-Alder and cope, and there's all this new material. That's what I would get my handle on first, but, hopefully, a lot of the reactions that you've been sort of accumulating, you're sort of keeping in the back of your mind, so. So it's going to be, okay, the next exam will be focused on the material. So the emphasis will be on materials that we've learned since the first exam. So we've learned a lot since that first exam. There's been a lot of important things. And so I've got a lot of material in there to put on the exam. And so the emphasis will be on that. And so if all you know is the material from that first exam, you'll be in okay shape. But there will be material from, you'll need to, it's additive, so you'll need material from others. Specifically, I would say in a synthesis problem. That's more likely where you're to see the past material, but I'm not going to guarantee that, other things won't creep up because I think that it's important that you guys maintain that knowledge. Yes, and then yes. Okay. Yeah, no, I noticed that. So like the phosphate-based, the sort of reduction. Yeah. If I sort of didn't go over it or something similar to it on the board, so like taking an aryl halide and reducing it, right? That mechanism I think I mentioned isn't even really known. You can think about it like a hydride. Yeah, we discussed that. Sure. Yeah, I mean, we went over it in class, but the reduction with LAH of an azide? Yeah. Right, so yeah, I mean, yeah, we went over that in class. I think it's certainly one that I think you guys should be able to think about. Now, again, I mentioned the mechanism isn't going to be exactly like this, but if you take an azide, we discussed, if you take an azide and treat it with lithium aluminum hydride, what's the product it's going to form? Yeah. Right, so this will get an H2, and the byproduct will be then nitrogen gas, right? So, right? And so we said anytime we talk about hydride sources, lithium aluminum hydride, sodium borohydride, these sort of reducing hydrides, right? Granted, it's not a complete hydride, but I sort of told you guys you can at least think about the mechanism as that sort of hydride. So if you're drawing a mechanism that involves LAH or sodium borohydride, to sort of help you think about it, they're all quote-unquote hydrides. And so from a mechanism standpoint, it's okay to just, for you guys to sort of rationalize it, is just to consider the hydride source as being the nucleophile, right? Oops. Yeah, thank you. So with a mechanism like this, the sort of question becomes, how might it react with this? And again, there's a few different mechanisms that we could draw here. But one of the things that you might want to consider about this is treating it, again, where did we very first see LAH? Carboxylic acid, carbonyls in general, the reductions of carbonyls, right? Where we first saw LAH, right, was sort of in the reduction of carbonyls, right? And so we discussed it as, at least we can think about it formally, as that sort of reduction. And so as we look at this azide here, we can draw a parallel with carbonyl reduction, right? So we have this sort of nitrogen-nitrogen positive charge, and in the same way that we push the negative charge on the oxygen, we can think about a similar mechanism where we can help take care of that positive charge on the nitrogen there with the hydride, right? Again, the mechanism is probably a little bit more complicated than this, but I think this at least helps explain it a little bit, which is one of the important things about mechanisms, right? To be able to convince yourself that this would do this when we can. Sometimes it's a little bit too complicated. And then we get to this point, and again, so we've gone from this neutral species now to take on this negative charge, and one of the things that we often do in a mechanism, right, it's sort of often discussed in the past, when you have a positive charge or when you have an acidic mechanism, right, oftentimes what you'll want to do is put a positive charge somewhere and then shift that positive charge somewhere else, and it's sort of that positive charge that is sort of moving throughout the mechanism, or meanwhile a negative charge, that negative charge is moving throughout the mechanism. So what you want to zero in probably here is that negative charge there, and think about how the electrons that are effectively represented by that negative charge may in fact be pushed away. And again, as you see nitrogen as being a sort of a leaving group, right, then what's going to happen here is now you'll have the amide. And again, once you take this and you treat it with water or whatever, now you're suddenly going to pronate it. So during workup, you're effectively going to pick up proton from something like water. So again, it shouldn't be, I don't know exactly the mechanism that takes place. There's, in other reactions, like I showed you guys, the Staudinger reaction, for example, that's a little bit more complicated one, and you're not responsible for it, but it actually attacks this nitrogen first. And so it's possible that the mechanism could be slightly different, but at least this is a direct way that should make sense and should at least rationalize why and how you might get that reduction. And again, it should be kind of parallel in many ways to just your sort of reduction. That's the point that I want to make, especially when you start bringing up older organic chemistry. Well, the hope is that if you've looked at new chemistry that you're learning and based upon previous chemistry, you're both helping understand the new chemistry and reinforcing what you've learned in the past. I think there was another hand up first.
Yeah, no, I want to ask about compound.
Okay, did somebody have a question about this specifically? Was your question about this? Yeah.
Yes. Compound hydrogen doesn't have the effect of nitrogen that's positive.
So who wants to answer that question? Question is, why doesn't the hydrogen directly attack this positive charge? Yeah, it's not going to help you at all, right? Because if you suddenly add the hydrogen, if you just want to add a hydrogen there, a hydride there, now you've broken the octet, right? So you'd have to push electrons away from it, which wouldn't help with the positive charge, right? So let me just explain that in another way, just graphically, right? If you have right, this is sort of a common issue, right? What you want to do is this. Right, what you want to do is that, right? And obviously you can't do that because now you've broken the octet. So effectively, once you add to that hydrogen, well then you got to move the electron somewhere else. And then you're going to be back to having a positive charge there anyway. So anytime you have a positive charge, particularly on like a pi bond, you'll push it to the adjacent atom such that the electrons from that pi bond can then go onto that. And the same way here. These electrons, which help that. Felix first. Say that one more time? No. Not sure where it's going to become positive. Are you saying you're trying to push electrons in the other direction? Right? No, that's not going to be positive. No. Yeah, it's got 4 bonds, you're right, but what else does it have? A lone pair. So you've broken the octet. Right? Conservation of mass, conservation of charge, right? If you try to push the electrons there and stop, I can see how you might assume that, okay, now it's got 4 bonds with positive charge, but what you're forgetting is that there's already lone pairs there. So that would actually, so again, conservation of mass, conservation of charge, right? If you go from here to here, right, the overall system has to stay negatively charged. You're not going to suddenly push electrons and make a negatively charged species suddenly a positively charged species without some other thing that's taking on and helping balance that charge set. So this would be negative, and it would be horrible, right, because we would have broken the octet. Make sense? So when you push them that way, you've got to keep going. Yes? Very much like carbonyl chemistry, yeah. Exactly. Exactly. That's what I'm saying, is that when you're in the same way that yeah. And you could also push, one thing that you could do is you could do it stepwise as well, right? You could imagine the positive charge in the same way that carbonyl chemistry sometimes we think of as, right, as this sort of resonance form. Sometimes we think about carbonyl chemistry happening through the cationic form just to sort of illustrate that this is where the bonds are coming. You can imagine the same thing here as well. You can first push the electrons onto there and have, even though that won't have a full octet, that's fine. Like, that's not breaking It's not breaking the octet rule. You know, breaking the octet rule is adding more. You can always have less, it's just not going to be as stable. But certainly that will often illustrate something. Okay. Any more questions on this one before we move on to, you don't want to ask about metathesis now? Okay, some other time. Okay. All right, more questions. Yeah.
Yeah, there was an example on your worksheet where bromobenzene reacts with protein and triplet acid and position.
Yeah.
I wanted to ask about the Lewis acidity of like a car relative to a carbocation generator. Why more? Does one happen more than the other? Are they identical in this sense?
Let me just get the question up there. So it was bromobenzene
Yeah,
reacting with propene and some acid.
TFOA.
Yeah, so triplet TFOH is, sorry, that's triplet acid. The triplet acid is a sulfonic acid, it's just a super acid. That's triplet acid. Triplet acid's got like a pK of like minus 14, negative 12. Corrected. Point is, it's a super acid. It's like you don't get much more acidic than triplet acid. So the question with triplet acid is, you know, it's gonna do really good stuff. So what was your question? Sorry, I didn't even.
I know like the Lewis acid, how would it act?
Yeah. So what this is going to do is it's going to react with this to sort of make right. So right, to make the secondary carbocation exactly. So and that's going to help. And now that's going to serve as our electrophile in the same way that, again, that was, even though it's not exactly how the mechanism goes, I was trying when we were discussing Friedel-Crafts style electrophilic aromatic substitution, I tried to sort of cluster them all into cationic character electrophiles to show that they're really good electrophiles. And we did glance over this a little bit. We said that alkenes and react with acid will also form cations, and those can also behave as the electrophilic source. So I drew the parallel between those and Friedel-Crafts acylation and alkylation in terms of cationic-like electrophiles. So that's exactly what's going to happen here. Now, some of you guys have asked, I guess in the book it talks about like how deactivating groups won't allow for things like Friedel-Crafts to take place and stuff like that. I wouldn't worry about that. I didn't really bring it up, so don't, as you're planning synthesis problems and stuff like that, I think I've probably even shown examples that the book might say don't work. But I wouldn't worry about the deactivating versus making something no longer happen. I would just more focus on the regiochemistry. That's the point that I want to emphasize, is that you can do chemistry. I don't want it to be confused further by reactions not working because there might be a deactivating group on there. So, is that all?
Yeah.
Okay, so if we follow this through, right, what would the bromine do? It would do ortho or para, right? And so the products that we're going to get are things like this, where right we have the sort of isopropyl group there, the ortho or the para position. So we get some mixture of those. Yes. Yeah. So if it's triplet acid, right, you just re-aromatize by regenerating triplet acid. Yes. So great question. Okay, so in a synthesis problem, the question will often come up, and actually we didn't bring this up in class, so I'm glad you brought this question up. The sort of question comes up is when you have an activating group versus a deactivating group, which one takes precedence? And I didn't bring this up, but certainly it will complicate any sort of synthesis problem. So if we have a situation where we have, say, for example, a nitro group, and we have, say, an ether, right? And let's say we went ahead and we took this molecule and we treated it with, say we took this molecule and we tried to do Friedel-Crafts with it. All right, so we did our acetyl chloride as well as AlCl3, and we want to functionalize somewhere on here. So we're going to put an acyl group either here, 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 here. So there's really 4 positions, right? And so what we basically do here is to sort of, what ends up happening, again, I don't know if this is always the case. I'm not as familiar with aromatic chemistry as I am with some other things, so my guess is this probably is an oversimplification. But to help you guys organize which one would work first, what the book says is that directing, the sort of orthopara takes precedence over the meta-director. And that might make sense, actually. If you think about it a little bit more, resonance and the sort of idea of full octets and stuff like that often takes precedence. And oftentimes, the ability of a directing group to direct in a certain way often has to do with the ability to have a molecule which has a full octet. Whereas if you go through the meta, it's often not the case. So, so I would say, if we think about our nitro, and we think about our sort of our donating groups, so right, so the donating group would be here, 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 and here, right? And then in the case of the nitro group, it would be here. And so this you would likely get a mixture of products, here, here, here. If you were to guess which one would be major and which one would be minor, you could probably come up with a hypothesis, and you might say that this position, because hysterics might not be as likely, but certainly you might imagine getting some there as well. So there would be 3 likely products, one of which you might imagine would be minor, but again, we didn't really discuss that. So I would, if you showed 2 positions, that would be fine. If you showed 3 positions, that would probably be fine as well. So, okay. Yes? That's a good question. So you probably want to look at the group. So the question is, same situation, but let's say that you have... What do you mean strong? Like, okay, so like, I mean, if this is like an OET and this is an OME, then you're just going to get a mixture and they're all going to be the same. There has to be some differentiating difference between the two. One's going to have to be able to stabilize that charge and be a little bit more nucleophilic than the other. So here's an example where we have 2 fairly strong ones, right? So we have a dimethylamine, right? And we have a methyl ether. And so, oh, did I do a bad job here? Wait, hold on. I think I want to put it here, right? Yeah, sorry. So let's do this. Right, so if we sort of think about this, we'll make this one green, and we'll make this one blue. Right, so in the case of the blue one, obviously we can't go there, but we can go here or here. In the case of the nitrogen, right, we can't go here, but we can go here or here. But the question really becomes which one of these would probably be a better stabilizer of a positive charge through resonance? The nitrogen, right? Why? Because nitrogen is more readily available to take on a positive charge, right? Amines are considered bases because they can take that on. So yeah, so if we were to do the same thing here, you would just sort of look at the two, and you would want to make some argument based upon actual chemical principles. And in this case, a nitrogen versus an oxygen, you would assume that this would trump. So you'd get here and here would be the preference. Does that make sense?
Okay. The orthopara of the nitrogen.
Orthopara of the nitrogen. Yeah, so again, this is just one example. I think that the point to take home is that you look at both of them and you ask yourselves, what makes it an orthopara donor? It's the ability to effectively stabilize through resonance, right? Mm-hmm. And then you just ask yourself, what's a better resonance stabilizer? What's going to be more likely to take on that positive charge? So you can imagine doing the same thing with, say, for example, I'm not sure what like an acid. Right, so if this was a nitrogen, then which one would be the better donor? What's that? If this was instead... Oh, yeah, even more so, right? Because methyls isn't nearly as good of a donor as a methoxy. If it's a methyl versus an OME, then it's going to go the other way. Now it's going to go this way, right? Because the OME is a better donor than this one. This is effectively stabilized by having a tertiary carbocation, right? This one is stabilized by resonance into the oxygen, so it's much better, right? Yeah.
How is it? If you're trying to decide, let's say, try a substitute benzene, or like TNT must be a product.
Okay.
Would you have to do, let's say, titration 3 times, or would you
Okay. Yeah. So the question now. So the question is, if you're trying to do multiple substitutions of the same group. So if you want to do Friedel-Crafts multiple times, if you want to do nitration multiple times, if you want to do sulfonation multiple times, bromination, whatever. That's probably going to be a stoichiometrically driven process. So you don't need to add bromine and FeVr3, brominate one position. Add another, then work it up and then add a whole another one. You would just let it go longer. You would add more compound. So in a synthesis problem, if you don't even need to put down equivalence. If you just show that you're planning on brominating it twice, as long as it's a rational way to go about it, and I can imagine both those positions being halogenated, then I'll give you that. It's fine. So generally 1 through 3, I guess. You could do any one of those. Yes. Weak activating group, yep. Strong deactivating group. Yeah, I mean, in that case, I see where you're going with that. I would just stick with the trend. The activating group is better. I would imagine that in those cases, the actual, again, I'm not as familiar with aromatic chemistry, so for your guys' sake, I would just stick with the book. I would just say the activating group is going to be more likely. So.
The book also said, you have a very, CL, with the strong deactivating, you still go,
So hold on a second. What?
you have a weak deactivating.
Right.
Strong deactivating, you still go with deactivating.
Yeah, that doesn't make sense to me. Yeah. Let's just say that's not going to come up in the exam. Because I'm not familiar with that. Holly. So the mechanism for so NaNO2 HCl. Oh yeah, you're thinking of okay. So I think the one that I had was something like this, right? Yeah. Right. Okay. Something like this. Yeah, so this is sort of a two-part question, right? Yeah. So that would be one possibility. Yeah, I mean that would be one possibility, which would be legitimate based upon your sort of thought. So if you sort of gave an epoxide mechanism, I think that's rational. That's oftentimes why I like to ask for the mechanism that you're asking for, because if it makes sense chemically, that's fine. If I gave you the product, though, and then asked you the mechanism, I'd want it the other way. I wouldn't suddenly want you to know the epoxide. So the question here is, what's happening here? What I was intending on this being is like the pinnacle rearrangement, but a lot of people are bringing up the epoxide as a possible alternative, and I would say that certainly the epoxide could also form. And it mechanistically would make sense. So, Holly, the sort of question is the entire mechanism. Do you want to just go through the whole mechanism? Okay, so when you take NaNO2 and you treat it with HCl, right? Sometimes it's HNO2 as well, but there's a couple different mechanisms that I talked to you guys about. I think perhaps the more direct one would be that what you're going to form, right, is a yeah. Okay, so something like this, right, where you have again the sort of cationic electrophile that we've seen so often in electrophilic aromatic substitution. So again, that's simply going to be protonation, elimination of water. So you can look back at the book for that one. And then what's going to happen, right, is that the nitrogen is going to attack this. And you're going to get to this intermediate here, right? It's going to have a positive charge on it. Okay. Then what's going to happen is a series of proton exchanges. So we're going to proton exchange over onto this oxygen. Right? At this stage, what we can do is we can undergo the resonance to show that this positive charge on here can be shared with that nitrogen, right? So we can imagine a resonance form here. Okay. And again, there might be other ways to get here as well, but I'm just sort of right, so you basically see what I've done. I've sort of pushed a resonance form, push that positive charge over onto the nitrogen. Again, then we're going to get another proton exchange. Right? And then this is where we finally get to that key diazonium species, right? Where now we're going to actually lose water. And so this is the first, this is the product that at the very least I would have expected you to get, and I would want you to get to here. But the problem was asking to take it a little bit of a step further. So this would be the mechanism, that first mechanism of forming the diazonium. Now, as the structure is sort of shown, with that alcohol there, what you might expect to happen is something else, right? And what was sort of brought up is, there's sort of confusion of exactly what could happen. Now, if we have that species, the first thing that you would want to think about is you're going to liberate nitrogen gas. And because that's oftentimes where we see these diazoniums. We almost see them as being super, super good leaving groups to the point that we leave behind cationic species. And so what you can think about right off the bat is the nitrogen gas leaving. To generate that cation. And what we learned about the pinnacle rearrangement is that once you generate that cationic character, what can happen is you can do alkyl migrations, right? When you have that cationic character adjacent to a carbonyl, to an alcohol, what can happen is you can get that sort of rearrangement product. Now again, what was brought up was, well, could you also do an epoxide, right? Where perhaps the alternative mechanism, you can imagine something else happening, and I think it's perfectly legitimate to expect that this might also form, or that could form. Again, that's going to be a reversal process, but I think at least in terms of my expectations of you guys, in terms of thinking about mechanisms and what could legitimately happen, I think that that's perfectly legitimate thought that it could do that. So, Felix. Okay. So first of all, I've made extra sure to not make this exam as long as the last one. And I think I gave you guys a little bit more room. Probably not. But you're really, really good. 20 minutes? 40 minutes? No, I mean, it's not going to be, it's not going to be. I tried to make it a little bit more. Well, we'll see. We'll see how it goes. Because on the downside of a more condensed exam is that there's less opportunities to get points, right? So there's sort of the double-edged sword, right? On the one hand, you can't get to everything, but in the meantime, there's not as much, so there might not be as much in there that you know. So, anyways, the point that I would say to you, Felix, is what I would do is that if there's a situation like this where you know that these form this intermediate, if you're rushing through and there's not much time and you're paying attention, what you could do, or say, for example, it's the beginning of the exam and you want to just get to the final product, you can shorthand like this, but you're probably not going to get full credit. And so what you may want to do is show this way, and then when you have time coming back, just show how this goes to that, right? Like in a separate box. So that would be my advice. I'd like to give credit to the people that have more full explanation, but specifically if you're running out of time and you're just trying to get to the final answer, to sort of show that you know that this goes to that, that's okay, but just go back later on. And again, if everything else is good, and a question like this, I'm not going to start giving out a rubric of what I would give, but you would get a very healthy percentage of the points, but you wouldn't get nearly as much. You wouldn't get as much as the person that had the complete mechanism. So just use your time wisely. If you think you want to get onto further questions and come back later on, I think that would be the strategy that I would take. Yeah. Well, I think somebody else had their hand up first. Yeah.
I have a question about like intermolecular effects. So like we're using the oxygen to determine, right?
Mhm.
But I feel like what I learned is like that doesn't have too much strain. So like you've got to have an outside molecule.
Maybe. Yeah, so the question that's being brought up here is a question of sort of thermodynamics. The recognition that every step in this process is reversible, and thus wouldn't the product perhaps go to the most stable product. So I guess what you're saying is that, well, this will be reversible, and this seems to be more stable than this. So given time, wouldn't go to this product here. And certainly epoxides, under acidic conditions, one of the things that epoxides do is they open under acidic conditions. Right, and so epoxides will open under acidic conditions. So you might imagine a mechanism where we started with this epoxide. That'd be a fantastic exam question. Start with this epoxide and treat it to acid and get this product here. Yeah, but I mean, you guys should be able to do that, right? Like if you started with an epoxide and then the product was the one from the pinnacle rearrangement, that'd be a Professor Morelli style exam question. But yeah, it would based on that. It would have the reversibility of that. And that's the biggest thing that I ask you guys to really do, is to be able to push mechanisms, be able to understand mechanisms, at least be able to propose things that at least what we call paper chemistry would make sense, even if it might not actually work if you did it in the lab. I think that's something that you graduate to once you're actually in grad school. Yeah. You could get the epoxide as well, or so you can get the diol as well. But if I said no other water around, right? If there is if it was under an aqueous solution, yeah, you might get the diol. Because acidic conditions, just okay. Well, that's kind of a general comment, right? So, but what else is in there? So yeah, if you had aqueous acidic conditions, you'd probably generate the diol. I think that's probably a mechanism we discussed in organic 1. If it was the acid and it was, say, anhydrous, so there's no water in there, then you might more likely have a chance to rearrange to that product as well. And I've seen in syntheses, like in papers, people doing that, going from the epoxide to formerly the pinnacle-like product. So people do that. That's a strategy, starting from epoxides and going to pinnacle-like. I've seen that in papers. So, yeah.
What is left here? HCl is a catalyst, but we generate water and by making microbial. Would you say, but then
Right.
water is higher than acid. Would you say the acid, the HCl minus catalyst?
Yeah, well, you wouldn't formally, under HCl, you wouldn't actually ever formally have, I don't think. Yeah, I mean HCl, pK of HCl is like -7, pK of H3O is like -2 or so. So you have pretty much H3O plus Cl. I mean, that's really what an aqueous HCl is, right? It's not, HCl is a gas.
Sure.
So formally, if you have an aqueous HCl solution, really what it is H3O plus Cl minus in an aqueous solution. But yeah, I mean, this comes back to what was just being asked earlier. It's like these are, if you have a lot of water, maybe. If you don't have much water, maybe not. And this is where I think that having hard and fast rules to that is kind of counterproductive. Recognize that both could happen, and in reality, depending on the conditions, different things. So as long as you can think about something that's rational given what's at your thing, I think we're good. There was one hand up before Felix. Who had their hand up and then put it down? Okay, I guess you're up, Felix. Say that again? Hmm? So the question is, if you have a chloro, so in aromatic chemistry,
Yeah.
so if you have, so you want to have nitrobenzene? And chlorine, or rather chlorine, I guess, here. You want to know where the reaction, like if you did. Yeah. So what do you think? What do you think it would do? It would go for the chloride. Yeah, it would go to the. I think that activating, deactivating. I think what's more important is sort of orthopara versus meta. So I would just go with the orthopara rule. And again, you could like what I said earlier. The thing about halogens is that when you start drawing those resonance forms, what you can do is you can actually draw intermediates that have full octets. And sort of having full octets is, while it's not, you can certainly draw intermediates perfectly well that don't have full octets. Generally, if you can have a full octet, that's hugely advantageous. And so the fact that orthopara directing goes through intermediates where you can satisfy unfulfilled octets by fulfilling the octet and putting the positive charge onto the halogen, that's going to be beneficial.
Because the text says that chlorine is quickly deactivated, while nitrogen is more quickly deactivated.
Yeah, well, that's what I was saying, is that it's better to think about orthopara being better than meta, donating groups, right? And again, back to that resonance. Yeah, they're both electron withdrawing, but certainly back to what they were saying, you can also make the argument, but that's a big difference, right? I think what was being asked before was something like this. Sorry, I understand where you're going. I think what was being asked before was something like this. Right? And again, I don't even know what the difference between these two would be in terms of deactivating. I think the nitro is more deactivating. So the question would be, which one of these would trump in terms of meta donation? And again, I'm not even sure whether you guys would be able to predict this, because I'm not sure that you guys would necessarily know which one is more deactivating. But this one's more deactivating. It is this one. No, I know that because I've worked with aryl nitros and aryl acetates, but I'm not sure that would be necessarily something that I would expect you guys to know. But yeah, in a situation like this one's the better deactivator. So I would assume that would trump the process. The way to think about it is if you're sort of up against the wall and you're in a situation like this, I think what you can always relate these questions back to, and again, it's the whole reason why I make sure that you guys really understand mechanisms, is you can equate it back to the resonance forms, right? If you think about a situation where you are, actually, I don't know about that now that I'm thinking about it. I guess I was thinking about nucleophilic aromatic substitution. But in the case of electrophilic aromatic substitution, yeah, I actually don't know the answer to that. I don't know the answer to that. I'll admit, I don't, yeah. I would say, and that's what I said earlier, I won't ask a question like this because I don't know the answer. Yeah.
So is there a situation where there will be a new reaction?
Oh yeah, no, but I told you guys not to worry about that. So yeah, certainly the more electron withdrawing groups that you have on an aryl group, the less likely it's going to be to behave as a nucleophile. Certainly. But I told you guys not to worry about that. I'm more concerned about the regioselectivity. And again, you guys have brought up a scenario that I'm actually not really that sure of. But I'd be curious, I think I'd be curious to hear what you guys think. To try to come up with a rational reason why one would be versus the other. And again, when in doubt, you can always break it down to mechanisms. So we can make an argument for this, and we could try to make an argument here. But I think you could go in one of two ways, right? I think that there's two competing arguments. If the question becomes which one is the better meta director, then you might say, well, it's going to be the one that's going to more likely stabilize the sort of negative charge. It's going to be the one that's going to create a greater dipole towards putting a negative charge here and a positive charge here. And so the argument can be made that this would be overall more likely to dictate meta directing. And so that's probably what it is. That would be what I think my gut would tell me, is that you would, because it's more greatly influencing that process, then it would sort of trump it because it's stronger. but truthfully, I'm not sure. There might be an argument in the other way as well. So it won't come up, but it's good to think about, I think. Yeah. Sure. Okay, so the question is stereochemistry of Hoffman and stereochemistry of Cope. And so these are instances where we have two different so we've got our Hoffman, right? So we've got our Hoffman elimination. And then if I draw the same thing, and I do a Cope elimination, okay, so here's two sort of analogous elimination processes where one's going to lead to one form of this alkene and the other one's going to lead to the other form of the alkene, right? So which one's the Hoffman? This is the Hoffman, right? This is the Cope, right? Now in terms of an elimination process, what's the distinguishing factor between these two? This is going to go anti, this is going to go syn. As drawn, are either of these set up to undergo the elimination that we're talking about without having to redraw it? Right. Why? Because this bond, right, is syn to this one over here. So I've sort of drawn it. It's already lined up in the syn conformation. And so again, in this transformation, what's going to happen is you're going to pluck that proton off, making the double bond, and then again, your leaving group is so it's effectively the same thing, except your nucleophile is internal. Or sorry, your base is kind of like the nitro, sort of internal. Okay? So when we do this elimination, everything that's on the same side during the elimination is going to be on the same side as the product. So the ethyl and the methyl group are on the same side. So when you draw the product, and again, you can draw it with them coming towards you, or you can draw it, the point is they're on the same side. So I usually like drawing alkenes without dashes and wedges. So again, this ethyl and this methyl are on the same side. And on the back side, you've got a methyl and a proton. Okay? Now, as you might imagine, if we do the anti-elimination, we're going to do the opposite. But let's convince ourselves of that by actually redrawing it, going through the anti-elimination. Okay? So if we want, what's that? This is the Cope. This is the Hoffman. Okay, and so now in the case of the Hoffman were actually not set up in the appropriate alignment to actually do the anti-elimination, right? In the anti-elimination, what we need the proton to be anti-periplanar to the leaving group. Remember, this is an E2 elimination process. Now, as drawn, some very observant student might say, oh, actually, you're not going to generate this product, right? Why? Why? Right? Because this is the more accessible proton. But give me a break here. I'm just trying to show you the stereochemistry and the stereochemical difference. So you see what I'm saying? In a true, what I'm about to show is simply to imply the stereochemistry. So I chose a bad example perhaps to do that because likely this would undergo the elimination here to generate the more exposed. But if what we're trying to do is draw the parallel in terms of Cope versus Hoffman for stereochemistry, which was your question, we can just show the other one just to sort of illustrate that the stereochemical potential differences if you could do the Hoffman this way. Okay? And so what we need to do, and this is more standard for any E2, right, is we're going to need to rotate around this bond, right, to put the proton down. Okay, so I'm going to make one point real quick, because I'm about to draw this up here. I want everybody that's in here to write down, this is technically not the product in a Hoffman, because I don't want you guys coming to me in a week and saying, oh, Professor Morelli, you showed us that a Hoffman would go the other way. So this is actually not the product, we're simply showing it for stereochemistry, because I know sometimes you'll show me your notes and it will be a little bit different. So just pay attention that this is simply to illustrate the difference in stereochemistry and how to go about thinking about stereochemistry of eliminations. Okay? It's not be the real problem. When we rotate around this group, right, we need to have the proton and the leaving group anti-periplanar to one another. Okay? When we do that, what's going to be coming towards us? Methyl. Which means that the ethyl group is going to be going in the other direction. Thus, when we do this elimination with the hydroxide base, now it's the methyl and the methyl that are on the same side, and it's the ethyl and the proton. However, what would really form, again, would be this. I don't want you guys to get confused. What would really form would be this in a Hoffman, again, because okay, again, I just wanted to show these two really more than anything to illustrate the differences between a syn and an anti-elimination in terms of the stereochemistry. And again, perhaps the Hoffman elimination isn't the best one to illustrate that because oftentimes it'll go to the external alkene where there's not actually any stereochemistry anyway. Okay? We've probably got time for one more quick question. Yeah?
So when you're doing that chemical reaction, is that concerted? I don't know.
You mean the leaving group? Yeah, I mean, yeah, so concerted or sort of, what's the other term? Concerted or asynchronous, is that what you call it? Like stepwise? Yeah, I mean, it's, you know, it's probably, it probably depends upon the stability of the cation that you could generate. If you mean from here to here, those are just resonance forms. If you're talking about from here to there, if I just did the migration first and then did the resonance form, that's the same thing because you're just going to the same product. Whether the leaving group is going to leave at the same time as the rearrangement is going to take place is going to be based upon probably the likelihood of the stability of that cation. If it's a less stable cation, then it's probably not going to formally form. This is something that you might see when you have that nitrogen being a leaving group, right? If the nitrogen is on, say, for example, a primary methyl group, the chances of you generating a primary carbocation are probably unlikely. But again, when it is something as good of a leaving group as nitrogen, there's certainly more of a chance of that happening than in other instances that we've seen. So I'm not going to necessarily penalize you if you show a primary carbocation with nitrogen being a leaving group. But that's the point, right? Is that nitrogen, we've seen nitrogen be such a fantastic leaving group that we've seen cations generated because of it that we hadn't seen previously. Cationic benzene, right? Like that the book talks about as kind of being the thought in terms of the intermediate. But again, that's because it's a special case. All right, again, exam is Monday. All right? Be here early. All right.